Okay, thanks, Ross. Actually, there's a typo in my original title. It should have been new variant hybrid, but that's okay. Basically, what I want to do today is I want to talk a little bit about some of the results that have come out of the REACT project, which is a European Framework 7 project where we've been looking at physical models for aftershock forecasting and seeing whether we can improve on basically the Coulomb rate state, which is kind of the standard model. And so just to remind you, there's sort of two end-member models for looking at aftershock rates. There's a physical method based on these Coulomb stress changes and rate state, and Ross and Shinji have done a lot of work on that. And then there's statistical models that we've seen introduced today, so STEP and ETOS, and I'll talk a little bit about STEP later. So the thing with the physical models is that they're quite parameter dependent, and you're really based on getting you really depend on getting the Coulomb map right, and that isn't necessarily easy. And so this is a slide that I stole from one of the other REACT participants, GFZ and Camilla Catania. And basically, this is just illustrating some of the uncertainties when you go to make a Coulomb map. So that you have to resolve the stresses onto planes with a particular orientation, and you don't know that orientation. So you can do optimal oriented planes, you can choose structure, you can make some type of decision, but you do have to make a decision. And as you can see, just looking at the focal mechanisms on the left, there's a lot of variation, natural variation, in the receiver faults. There are also a lot of errors in the slip models, and there are two types of errors. One is simply a scaling thing, that the slip models may be done on a resolution of 5 kilometers by 5 kilometers, and yet we know they're small-scale slip. The other, and we show this on the poster downstairs, is that when you look at various published slip models for the same event, they look very, very different. Which one's right doesn't matter, okay? And in Coulomb rate state, because the forecast rate depends upon the magnitude of the stress change, it does matter. And then finally, you tend to discretize your maps on a particular size, and yet you're then calculating a forecast with a value of the stress that may not be representative of the entire volume. So one approach to this is to explicitly include the uncertainties. And again, this is something from GFZ, where they're trying to put these uncertainties into the model and then create new forecasts based on this. And the testing of this will be shown in a poster by Max Werner downstairs, as well as many other models this afternoon. So that's one approach, and it's looking quite promising, and I refer you to Camilla's paper in JGR. Another approach is to combine the Coulomb model, the physical model, with the statistical approach. So Matt's already shown this picture, or one of these. This is STEP implementation in New Zealand. This is another STEP implementation after the Cook Strait events. And what we've been doing, and this is just reminding people how STEP works, it's got generic parameters and then parameters that are sequence specific as a sequence begins to develop. So what we've done, and we published this last year, is that we created a hybrid model, and we used the Coulomb map just as a very simple filter. So we said, if it's a red area, stress increased area, then it's more likely to have earthquakes, and therefore the rate is going to increase there. If it's a stress decreased area, it's less likely. So we got away from knowing the magnitude of the stress change, which is really difficult to calculate. And again, GFZ, we're trying to get around it in a more sophisticated way. The other thing that we did was we had a generic parameter here, and we assumed that 93% of the events were going to occur in the positively stressed areas. So that was based on some observations from California. How robust it is unclear, and you'll see some results in a second on that. So, and then we did a couple variations on this where we applied this filter everywhere, and one where we applied STEP itself on the fault zone. And then we compared this against STEP and also against one implementation of Coulomb rate state. So we applied this initially to the Canterbury sequence. Matt's already talked about this sequence, 4 events. And what we did was for each event is we used the first 10 days of observation to forecast then the seismicity in the next 100 days. And we compared these various models. And just to give you an idea of what they look like, the top 2 are the hybrid models, the combination of STEP and Coulomb, and so you can see distinct lobes No, here we go. You can see distinct lobes, basically here and here, which is consistent with the Coulomb pattern. This is step on its own. It's much more symmetric. And then this is a Coulomb rate state. Okay. So we looked at this, and we did this both pseudo-prospectively and retrospectively. And what we found was that pseudo-prospectively, we never did as well as, or we never beat step. Retrospectively, we did in some cases, but it really depended on getting the Coulomb map right. So what we've been looking at more recently is we've asked the question, well, what if we see how good our Coulomb map is and use that to guide the percentage of activity that we force into the positively stressed lobes? Okay, so kind of a simple idea, really. And so what we're doing now is we're saying, okay, in the first 10 days learning period, we compare the Coulomb map to the percentage of events that are triggered in, or that happen in those red areas in the learning period, and then we use that as our function, how much is going to get pushed into the red area in our forecasts. And so these are some results, and basically this is the old model. So we put 93% of the events in the positively stressed areas. This is a model where we calculate the correspondence between the map and the initial aftershocks in the learning period, and then alter that percentage. Okay? And this is the percentage that were observed to happen in Coulomb in positively stressed areas. This is after the Darfield earthquake, the Christchurch, the June earthquake then, and the December. So the 4 events. The color code's very simple. If it's red, the model did better than STEP. If it's blue, it did worse. And if it's green, it did the same with an error. Okay? So where you have a high correspondence between the Coulomb map and the aftershocks, then basically you always do as well as STEP, and sometimes you do better. In this one place here where only about 74% of the events occurred in the area that was red based on this particular slip model, then you did worse than STEP with the 93% assumption, but the same as STEP with the Vario model. This shows up a lot more when we look at this in terms of landers, and in the poster downstairs we're looking at the sensitivity of these types of forecasts to the the choice of receiver plane and also to the choice of slip models. And we basically made up a bunch of slip models that you might have had very early in the sequence. And so this is the same type of thing there, where this is the percentage of events that occur in the red areas, and this is a terrible Coulomb stress map. And the reason is that it was based on knowing nothing about the slip distribution, just knowing the magnitude of the earthquake and the focal mechanism, and you basically get the slip wrong, very, very badly wrong, you get the fault geometry very wrong. And so only 10% of the events actually occur in that area. So clearly if you make that assumption that 90% are going to happen, you do much, much worse. Okay? Whereas you do about the same if you push the events the other way, because you're actually essentially doing a backwards filter. Okay. So what's encouraging about this is that in all cases we do at least as well as STEP with this variable model, and in a number of cases we do better. And so it's almost like a doctor of doing no harm, that by knowing how good our model is, our Coulomb model is, before we start making the forecasts, then we're not going to make things any worse. Okay. And that seems a bit negative in a way, that we should say saying we're charging and it's going to be tremendously better. It's complicated, and if you look at Max's poster this afternoon, you'll definitely see that it's complicated. But just to try to pull this together, and again, this is things out of the REACT project overall, not just from me, is that we see that these physics-based models can improve the forecasting power compared to purely statistical ones. Matt asked the question earlier, have we hit a point of no return? Do we keep pushing down this road or not? I kind of think we do, but then I'm a Coulomb modeler. We do know that these models are very sensitive to various uncertainties. We mentioned some of those earlier, and we've got to take these into account in some way. And a couple of different approaches we mentioned today is what GFZ have been doing in terms of the stochastic treatment of the uncertainties, or alternatively of weighting the models based on their early skill in order to forecast their later skill. And then finally, coming back to the idea of ensemble models that we've heard earlier, I think it's very likely that a combination of these approaches and some type of ensemble models will be most appropriate. And then just finally, an advertisement, looking for a postdoc who wants to work in Australia for 3 years. Thank you.
Okay, questions for Sandy?
Getting off the hook. Uh-oh.
Shinji?
Sorry. How about the uncertainty of the hypocenter locations to test the Coulomb models, right?
Repeat the
Yeah,
question.
yeah. Yeah, so Shinji asked about the uncertainty of the hypercenter locations for testing the Coulomb models. I agree. It's a good point because you're saying how good are the models, but you've got location errors, so you're going to have uncertainty there, and it probably needs to be built in some way. Send that off to the smart people at GFZ. No.
So Sandy, your view is that we should be able to combine Coulomb static modeling and statistical modeling to try to forecast earthquake occurrence. Are you thinking also about dynamic triggering and how that might fit into this recipe?
I tend to avoid dynamic triggering, Ross, because I don't think the evidence is there that it's an important factor, except very, very early. You know, and I think something we need to think about are, again, what Matt talked about earlier, are models appropriate for the time of interest. And so I think, for example, the statistical models may be very, very good for kind of 24-hour forecasts. If you're going to forecast over the next 100 days or the next year, I think the physical models are more important. The dynamic stuff, you know, I think the model, the work by Massimo Coco and others, you know, have shown that it really is important early on, and I'm not convinced that there's a dynamic effect longer than that.
Thank you. Thank you, Sandy.